I'm Apostolos Giannousas, and my colleague Christopher Kirwan are going to discuss about our PRAISE HPC project, High Performance Quantum Fields. First of all, let's delve into an introduction, a brief overview, let's say, of what lattice quantum chromodynamics is. Actually, quantum chromodynamics is the ruling theory behind the strong interaction which makes the existence of hadrons like protons and neutrons possible. Their constituents, which are called quarks, are bound together by the strong force via particles called gluons. As given away by their name, gluons act like a glue for quarks. The term chromodynamics has to do with the charge associated with the strong force, the so-called Kähler charge, and it has nothing to do with optics, but it gives us a way to visualize the concept of this charge. The types or colors of this charge are red, green, blue, and their corresponding anticolors. Now, what you might ask, what lattice quantum chromodynamics is, as I mentioned in the beginning. Actually, in QCD theory, the main objective is the calculation of various physical quantities using the path integral. However, calculating these infinite dimensional integrals with perturbative techniques becomes incredibly complicated or even impossible at low energy scale required to describe nuclear interactions. Consequently, we resolve to lattice QCD, which is a non-perturbative formulation of QCD on a discrete Euclidean space-time grid, also known as a lattice. This approach makes QCD simulations on HPC resources not only feasible, but also highly efficient and accurate.
Hi, I'm Christopher, and so my side of the project was on benchmarking Lattice QCD using the Kokkos programming model. So, modern HPC systems have a diverse array of hardware, thus performance portability is becoming increasingly important, especially in the exascale era. Therefore, programmers must know how each architecture works and to write code that explicitly targets each platform, which is a very time-consuming and difficult process. So how do we solve this problem? One solution is to use performance-portable programming models. For this project, we have chosen to investigate Lattice QCD with Kokkos. Kokkos is a C++ template library that provides abstractions for parallel execution and memory management. The concepts introduced by Kokkos are execution patterns such as parallel for, parallel reduce, parallel scan, which are performed on execution spaces such as OpenMP, CUDA, AMD processors, all these weird and wonderful things, using such things like execution policies, so like team policies and simple for ranges. Kokkos views, which are just multidimensional arrays that are stored contiguously in what we call memory spaces. So this just generalizes the point of having a pointer to some sort of array. Kokkos provides backends for many shared memory programming models and has various optimizations for a variety of processors like NVIDIA's Ampere or Intel's Knights Landing, all these kind of different things that are provided in HPC centers, which could be turned on at compile time, just a simple command. This project was based on exploring the use case of Kokkos for Lattice QCD kernels, and in particular, the Staggered Dirac kernel. So this is just the equation for the staggered Dirac operator acting on a particular Quark site. This is actually just a staggered transformation of the Dirac-Wilson fermion, which reduces the number of Dirac indices from 4 to 1. Therefore, the Quark spinner goes from 12 complex entries to just 3 complex entries per site, which makes simulating these fermions very cheap. Although the problem is you have you do get discretization errors, and they're much higher in the staggered Dirac operator. Similarly, just you have some gauge links, which are just 3 by 3 complex matrices, and that forms 18 complex numbers. And this is just a sum over all the nearest neighbors on a site. The full Dirac operator has a dimension of approximately 10 to the power of 8 in most modern simulations, and is a very, very sparse matrix. Thus, we can use many sparse matrix iterative methods to invert destaggered and then get the Quark propagator out of that. So Why are we using Lattice QCD for our benchmarking? Well, to give a definition to start off with, memory bandwidth is the rate at which data can be read from and written to memory. For our purposes, we are using the stream convention, which is just a simple sum of the total number of bytes that are read from memory and then the total number of bytes that are written to memory. And so, unlike most other applications, benchmarking memory bandwidth in Lattice QCD is actually quite important, as most Lattice QCD calculations are very memory bound and not CPU bound, mainly because of the amount of matrix multiplications. So, for example, in double precision, we have 66 floating point operations per site, but we have 192 bytes read into memory, and then we have, or read out of memory, and then we have 48 bytes read into memory for each site. So this is approximately 4-to-1 byte to flop ratio, and this stresses memory quite heavily. So either memory bandwidth or network performance, such as intranodal communications like InfiniBand, are the main two limit on performance in Lattice QCD. So on a single node, memory bandwidth is the constraint. So this is a great test bed for Kokkos performance portability. So just to discuss a few basic results, we had a staggered Dirac kernel with lattice dimensions of 32 in the spatial directions and then 64 in the temporal direction. And the periodic boundary conditions are turned off, so that we just had an extra ghost layer on each dimension. It just meant that we got through our calculations much better and in a much more efficient manner. So we didn't have to calculate periodic boundary conditions at every site, which just reduced the memory throughput. So on the Eureka CPU from the Jülich Supercomputing Center, compiled with the Clang compiler with 32 threads, we got a rate of about 79 to 80 gigabits per second, which is quite high, and it's about 80 to 85% of codes that target these architectures very specifically. And then on the Eureka GPU, we got about 540 gigabits per second. So it shows that the Lattice QCD problems are very highly scalable and very highly parallelizable as well. And then just for fun, I've also included the results on the Ewell's booster, which is just a bunch of AMD A100 GPUs, and our theoretical performance is much higher, and we've reached about a sustained level of about 1,100 gigabits per second.
So my part of the project was to perform Hadron spectroscopy using LQCD. My actual goal was to try calculating a pion's mass and approach its experimental value. To do this, I utilized a tool called Chromoform for making Lattice QCD simulations. Initially, I did simulations for a specific input quark mass, but 20 different gas configurations. Then I extracted the pion correlators out of those simulations to find the average pion correlator and its standard error. Moving forward, I used the average correlator and its standard error for a specific quark mass to perform exponential fitting and acquire the pion mass by using GNU-plot, which also gives the standard error of this mass. However, GNU-plot does not consider the correlation among configurations, which means that its error estimate is somewhat inaccurate. Therefore, I replaced it by calculating the jackknife error, which is much more precise in this case. Last but not least, we did the extrapolation to find the target quark mass. And what this is all about is basically to extract a pion mass as close as possible to its experimental value. We need a specific quark mass. So let me explain this. The pion's physical mass is approximately 135 mega electrovolts and translates into the dimensionless lattice mass of 0.129. To approach it, I exploited the approximately linear relation between the square of the pion mass and the quark mass. Specifically, I rerun the same simulations with another quark mass, found the resulting pion mass, and used those two pairs to calculate the function describing the aforementioned linear relation. Finally, I plugged in the desired pion mass square of 0.0166 and obtained a quark mass of minus 0.087. The quark mass here is negative due to the additive mass shift introduced during discretization. Although I could get only as low as minus 0.07 due to the increasing difficulty for solution to converge, the resulting pion mass of approximately 0.245 got pretty close to the experimental value. So I will end my presentation with some plots. This is a plot which demonstrates the exponential fitting of 4 different quark masses correlators. And this here is a plot with the linear relation of a pion mass square and the quark mass. That was the relation we discussed previously. And the blue line here is the target pion mass square, which shows us the quark mass we need to, the theoretical quark mass we need to give as an input to our program.
All right, now time for some concluding remarks. So Lattice QCD offers extremely effective tools to explore QCD physics. Hadron masses can be extracted from path integral data using different field configurations, and then we can fit them using exponential plots. And then Kokkos provides excellent performance portability for applications in Lattice QCD. Thank you very much for listening.
Thank you very much for listening to me as well.